Now let's look at what are called higher order finite difference formula. We can obtain more accurate in a very precise way. On any given piece of data, they may not be more accurate, but in general they are. Finite difference formulas by using interpolation to get a polynomial fit to the finite set of values of f near x, and then evaluating the derivative of that polynomial, which is very easy to do, at x. And that will give an estimate for the derivative of f at x. Let's look at some of these formulas. Here is the formula you get when you fit a quadratic through the points x, f of x plus h, f of x plus h, and x plus 2h, f of x plus 2h. Here's the derivative estimate you get if you fit a quadratic through the points at x, x plus h, and x plus 2h. That would involve, of course, the value of f at those locations. If you carry this out with a quadratic interpolation and then evaluate the derivative at x, the formula that you get is expressed right here. It looks like a finite difference formula, but it's more complicated. It doesn't just involve f at x plus h and at x. It involves all 3 points, and they're combined in an interesting way, a -1, 4, 3 pattern. You can do the same thing doing a quadratic going backwards, x, x minus h, and x minus 2h, and then evaluating the derivative of that interpolating polynomial at x. And you get this formula. It looks quite similar. There's certainly a pattern of the alternating signs 1, 4, and 3. How about a quadratic centered at x? Forward x plus h, x, and x minus h. In that case, the derivative at x ends up not involving the value of f at x. And you simply get the centered difference formula. So the centered difference formula can be thought of as not a straight line fit, but it really is coming from a quadratic fit through those 3 points. That's one reason why we saw that the centered formula looked generally more accurate than the forward and backwards when we were considering the most basic finite difference methods. Finally, I'll throw out a quartic. This one is a centered quartic. All these can be derived, centered, forward, backward. This one is centered at x, x plus h, x plus 2h, x minus h, and x minus 2h. Interestingly, it also ends up not using the value of f at x. It only uses the 2 forward values and the 2 backward values. But I want to reiterate that this is what is obtained by fitting a quartic through those 5 points and then computing the derivative of that quartic at x. Here's the formula. As I mentioned, you can derive these for any pattern that you would like. It's just a matter of going back through the polynomial interpolation and carrying out the calculations listed. You can also use this approach, that is interpolation, for irregularly spaced data. The formulas get a little more complicated than what's presented here, where we had a spacing of h between all the points in question, but nevertheless it can be done, and you can probably look those up on the web. Let's try this in Matlab. Let's revisit the example with the exponentially decaying cosine. We know exactly what the derivative is. We'll use very sparsely spaced data, only 15 points between 0 and 3, and y data is of course the function evaluated at that. For comparison purposes, we'll compute the original finite difference formula, the forward and backward, using only 2 points. We'll also want to plot things very finely since we know the exact answer, and that's what xg is for. On the first plot, we'll plot the forward estimate and the backward estimate as well as the actual derivative. That will be a plot we've seen before. And then we'll move to the higher order formula. H is 3 divided by the number of data points minus 1. Here is the derivative using the quadratic formula. That's the 2 forward. It involves y advanced twice, y advanced once, and y all divided by 2h. The x data, since it was forward, is x data 1 through 2 points from the end. The backward involves y advanced twice, once, and y, but the x data is different. It's the x data with the first 2 points omitted. And finally, the quartic centered. I'll scroll over here, and you can look carefully at that formula and stop the video and look at it. 12 h's in the denominator. I have y going from 5 to the end, 4 to n minus 1, x goes from 3 to n minus 2, then y also goes from 2 to n minus 3 and 1 to n minus 4. The fact that this pattern is not shown in the y's is because in the quartic centered, remember the value of f at x doesn't matter. Only the forward quantities matter and only the backward quantities matter. The value at x is not used. Then let's plot these. This will involve the exact derivative on a fine scale plotted with a black line, then the forward quadratic with red circles, the backward quadratic with green pluses, and the centered quartic with blue stars. Let's slide this over and run it. Up top is the curve we saw in the past. The spacing is a little wider, therefore the errors are a little larger. Those are the basic forward and backward estimates of the derivative, with the real derivative shown in the middle. Down below, we see the estimates with the higher order schemes. We see that the accuracy is much better. The forward and backward are not symmetric because this function is not symmetric. So it has a little more action in the beginning, and it's much calmer at the end. That's why the backward differentiation is doing quite well at the end. But the one thing to notice is that the center is quite accurate, but the center is missing points at the beginning and the end because it needs 5 points before it can put out an estimate. The other ones only need 3 points. Therefore, there are 2 points missing at the end for the red forward and 2 points missing for the green. These schemes are clearly more accurate. We won't have time to quantify in this class the sense in which they're more accurate, but you can learn about that more in the classes that I'll mention later. In the statistics module, we will study a little bit about how sensitive these various methods are to small errors in the function evaluations, the noise mu I that we introduced in the slides earlier.